from IIT Madras. So my research interests include wave energy, solar energy, alternative fuels, and solar water desalination. Now today I am here to deliver a talk on power generation using a mechanical wave energy converter. Now, let me share the screen. So let us start the discussion. Now, today I'm here to deliver the talk on power generation using a mechanical wave energy converter. Now, see, if we talk about wave energy, what is wave energy basically? It is nothing but the concentrated form of wind energy produced by the progressive transfer of energy from wind as it blows over the sea surface. You see, basically, what happens? Ultimate source of energy is basically sun. Okay, from sun, then we get wind energy, and when wind energy blows over the surface of ocean, then it tries to pull water. Okay, and in that process, waves are generated, and now this energy in these waves is called wave energy. Now, if we talk about why wave energy and what are the benefits of wave energy, then most important benefits of wave energy are this is the most concentrated form of renewable energy, right? It is even more concentrated than your wind and solar energy. Now, time required for re-engineering the existing technologies applicable to offshore oil and gas, wind power and shipping industry is less because there are already existing technologies which we are using in exploring oceans regarding oil and gas exploration. So time required to have devices which can capture wave energy will be less. Now, the most important part then is there are many ideal locations in Europe, in North and South America, and then there is Africa, South Pacific Ocean, and Asia, where high power densities exist close to highly populated areas. Basically, you see, we need to generate power where we need it, basically. So, see, many major cities in the entire world, they are located along the coastal line, okay? So, then availability of wave energy is also there. So, this is good point. Then its nature is predictable and dependable in comparison to wind energy, right? Then next one, environment friendly. So you see every renewable energy is environment friendly. There is no pollution, no fuel is required here, no exhaust gases, nothing, no noise. Okay, so this is very interesting part here. Then scalable up to large power stations. If we can come up with a technology which can harness wave energy efficiently, then scaling to large power stations is not a very difficult thing. So this is another advantage here. Now, if we talk about this, what is the history of wave power? Then you see the first known patent to use energy from ocean waves dates back to 1719, and it was filed by Mr. Girard and his son in Paris, basically in France. So an early application of wave power was a device constructed around 1910 by Vaux to light and power his house at Rion near Bordeaux in France. Now from 1855 to 1973, there were already 340 patents filed in the UK alone. So you can see how many people were involved in research and development regarding wave energy. Now, modern scientific pursuit of wave energy was pioneered by Yoshio Masuda's experiment in 1940s. He was a Japanese researcher. Now, a renewed interest in wave energy was motivated by the oil crisis in 1973. Basically, in 1970s, there was huge oil crisis, and it forced researchers to look for alternative energy resources. So, in that pursuit, people started exploring wave energy. In 1980s, a few first generation prototypes were were there in sea, and in 2008 the first experiment waveform was opened in Portugal, right? Basically in Portugal the first commercial pilot project was launched. If we talk about this what we call a wave power potential for Indian coastline. Now, if you talk about India particularly, so in India, the research and development activity for exploring wave energy started in 1982. See, the whole world started focusing on wave energy after 1970s oil crisis. Now, primary estimates indicate that the annual wave energy potential along the Indian coastal is between 5 megawatt to 15 megawatt per meter. So this is good potential. Now, if we talk about theoretical potential for our country, now it is around 60,000 megawatt, and we have a 6,000 kilometer coastal area, coastline of length. So this is enough. And if even we harness 10% of it, now you can see we have some good potential for our coastal areas. Now, India is estimated to have a potential of 40 to 60 gigawatt of wave energy around it post the current state of technology. If we talk about whatever technology we have, so this much potential is there if we can implement that. But if we see, as far as commercial scale is concerned, there are no big wave energy plants in India. In fact, in entire world, still we are in R&D stage. People are exploring wave energy. Still we are in R&D stage. We have developed some prototypes and installed. So getting commercial plant is a challenge till date. Now, there are no big wave energy plants in India, except we have a pilot plant at Vizhinjam Fisheries Harbour near Trivandrum in Kerala. So this was a pilot plant which we installed long back. Now, Maharashtra government also built a project that would generate 15 to 20 kilowatt of electricity located in villages near Ratnagiri district. So if we talk about Indian scenario, so it is not very bright. Still, there is a lot of scope to do research and come up with techniques and technologies which can harness wave energy efficiently. So a long way to go as far as commercialization of wave energy in India is concerned. Now, if you talk about wave power potential for the entire world, now see, we talk about this 2 terawatt. This is huge potential as far as worldwide resource of wave energy is concerned. Now, locations with the most potential for wave power include the western seaboard of Europe, northern coast of the UK, and the Pacific coastlines of North and South America, Southern Africa, Australia, and New Zealand, Japan also. So there are many countries which have great potential, and Europe is the, we can say final destination. Europe has great potential, and they are working very hard to harness this energy. In UK itself, people are doing a lot of work there in collaboration with the industry, and they set a target for 2020 in the name of do and die. So, but because of COVID situation, a lot of disturbances there. So let us hope after some time they will resume their activity on large scale. Now, north and south temperate zones have the best sites for capturing wave power. If we talk about United States in particular, then it is estimated that the total energy amount that could be generated along its coastlines is equivalent to 1170 terawatt hour per year, which would account to approximately 10 kilowatt hour per United States citizen per day. So if we see the potential, it is huge potential. Only thing we need to have technologies which can harness it efficiently. Now let us discuss some existing technologies which are there, which people have got patents and they have explored up to some extent. So first of them is oscillating water column here. If you see the diagram here, now see, this is an air turbine here, and this is a structure where waves are entering. And then once waves are entering here, there is air trapped, that is compressed because of this force from waves, incoming waves. And this air which is getting compressed in the process, that is passing through this air turbine and rotating it, which is ultimately connected with a generator and generating power. So wave energy conversion technology that comprises of a large steel or concrete structure that is partly submerged. The structure has opening at the bottom to trap air above the water surface. Topside houses an air turbine for power generation, and waves enter the device through the partially submerged lips that trap air upwards through the air turbine. Pressure thus obtained from the compressed air is used now to rotate the turbine to generate electric power. And then second was is Pellamist wave energy converter, very important technology because it was the first technology which was brought to sea on real site at prototype scale, and it worked wonderfully for 1.5 years almost. So this successfully generated power for a certain period of time. Now you see this here is nothing but this is an artist impression of 30 megawatt wave farm. This technology was installed in Portuguese water, and here see each Pelamis has three power conversion modules that generate power of the scale 750 kilowatt, right? So these are three power conversion modules, 1, 2, 3. Now length of this is 150 meter and dia is 3 meter. Now waves move across the sea and cause the Pelamis to rise and fall in a snake-like motion, right? So it works like this. Now sections move against each other on hinges resisted by hydraulic rams, driving generators to produce electricity. Now a wave farm would have 40 machines over a square kilometer generating power for 20,000 homes. So this was the first prototype scale technology that was installed in real sea conditions. Right now, let us say a video for 2 minutes, and I'm showing this video because this was the most important technology employed in real sea conditions. And with this video, you will get a clarity how does it work basically.
शर्म आ रही है उनके सामने बार बार निकालने अंकल के पास वही फोन है भाटे अंकल के पास भी
So this was the video which explained working principle of Pelamis wave energy converter nicely. Now next technology is Wave Dragon. Basically this is an ore topping device. Now you see working principle of this device is similar to your hydro power technology. Basically just like that we have a dam here, basically that is called reservoir here in this case, where we store water. Okay, incoming water in the form of waves from ocean or sea that is stored here in this reservoir. And when this water from this reservoir, when it is stored enough in sufficient quantity, then it is allowed to pass through the turbine at the bottom of the plant. And in that process, water passing through these turbines will rotate the turbine, and ultimately and that is coupled with a generator. And in this way, we can say a three-step energy conversion process, right? So what happens here, it elevates ocean waves to a reservoir above sea level. See, from the diagram, you can see clearly water incoming waves are given a direction, and they are topped over this, and they are stored here in this reservoir. Now, then once it is filled, then water is let out through a number of turbines, which are installed at the bottom of the plant. And in this way, we can say this is a three-step energy conversion process. Next one is Aqua Buoy. It is basically a point absorber, right? Now here it is a freely floating heave point absorber, right? This is a plot here. Now see there here, each buoy contains a pump that rises and falls with the waves. Okay, then this pump compresses seawater, which turns a turbine and generates electricity. Right now, the electricity is transmitted to shore through an underwater cable. Okay, now what happens here? Basically, a free-floating heave point absorber reacts against a submerged tube filled with water. So there is a tube here in this device, which is filled with water. So that acts as a reaction mass basically. So this system is reacting against this water-filled tube. Now it forces hose pump to pump water on a high pressure level through a turbine that generates electricity. The turbine is housed here. Now both in the upward direction, when it is going up and down, okay, so in both the direction it is generating power. Okay, so that is the advantage with aquabuoy technology. Now I will discuss about the mechanical wave energy converter, which I worked upon during my PhD work. Now this is a device which is purely mechanical, right? Now here power take is purely mechanical system. There is no hydraulic system, there is no air turbine, nothing like this. Okay, so now this is a float here, okay, that is resting on the sea surface. Okay, it is connected with this rack and pinion arrangement. Okay, when incoming waves are hitting this float, so it is going up. Okay, when it is going up, one section of this system is actuated and it is rotating, let us say clockwise, it is rotating anti-clockwise. Now when it is going up, this section is working, okay, rotating the device and generator ultimately. And when it is coming down, then this is rotating clockwise, this is rotating anti-clockwise. So during downward motion, this second part of the system is activated and energy is transferred through this system to generator. So what we can say here, in both the upward and downward motion of this float, which is activated by waves, incoming waves, is harnessed through this mechanism. Now, during the downward motion of the buoy, power absorbed by floating buoy is transmitted to pinion gear 6. Okay, and while pinion gear 5 remains idle due to free wheels, sprocket, and vice versa. Just like bicycle, this mechanism is just like bicycle. When you pedal forward in forward direction, a power is transmitted to rear wheel, and when you take it backward, then it is free. Okay, so that mechanism is used here, chain assembly basically, right? Now, what are the scope and objective of the present study? To design and develop mechanical wave energy converters for operational sea states, then to conduct failure mode and effects analysis for the newly proposed device to identify the risk and failure at component level. I won't discuss this concept here, that is FMEA, failure mode and effect analysis, to analyze the failure possibilities of a device, because then it will become very long talk, which I do not want. Now, to carry out the experimental investigation on the developed models of mechanical wave energy converters to compare the results, to study the influence of wave heights and periods on the power generation capacity of proposed device, and ultimately to compare the mechanical advantages of the proposed mechanical wave energy converter with the existing similar technologies. Now, what are the advantages of mechanical wave energy converter? It is simple and easy to fabricate, low cost device, low failure rate, because these all things are established. If you use this system for a designed wave height and time period, then failure rate is not issue about failure rate. The proven and time-tested technology of mechanical engineering are used in the design of the system, because gears, chain, all those things we design nicely because there are technologies for that. So there is no issue as far as failure is concerned. It can be installed at any location in ocean for the designed band of sea states on a fixed platform like jacket platform with little modification. Hence, no need of installing new platforms for. See, basically this device is proposed with the idea in mind that existing platforms are there to harness oil and gas in ocean. So in those platforms, we can have minor modifications and we can install these devices. And we can generate power, sufficient power to meet the electricity requirement of the platform. Now, I will discuss experimental investigation of mechanical wave energy converter. Now, in this present case, a 1:7 scale model was designed and developed to estimate its efficiency. and a floating buoy of 620 mm diameter and 500 mm height is used here. Wave film used for the study is equipped with a piston type wave maker. I did my PhD from IIT Madras, so we have a very good laboratory there as far as ocean related requirements are concerned, because in our country, IIT Madras and IIT Kharagpur, there are two IITs which are having facilities regarding ocean exploration. Now, it is capable of generating regular waves for a wave height of 5 to 30 centimeter with a wave period of 1 to 3 seconds. This is the limitation for this device, which can generate waves in lab. Now, a wave probe is fixed in parallel to floating buoy to measure the height of the incident wave. Because we need to measure the height of the incident wave, because we need to find out the incident energy at the float. So wave height is very important parameter, wave height and time period to estimate the energy available to the device. Now an accelerometer is fixed at the top of the rack to measure heave acceleration of the buoy. Now once we can measure acceleration of the buoy, so we can find out the force from the buoy which is available to the device. A dynamo and torque measuring devices are coupled with the output shaft of the device to record the time history of mechanical and electrical power outputs for various wave heights and wave periods. Overall efficiency of the device is thus estimated. Now, if you see this video, you will get clarity about the working principle of this proposed mechanical wave energy converter. So with this video, I hope you have got clarity about the working principle of the device. Now, mechanical power from the output shaft of the device is measured using the torque sensor, and the results are given below. So this is nothing but torque produced by the device. This is nothing but wave height. This is time period of the wave. Now, you see this for 2.3 second and 18 centimeter wave height, we get 3 watt. Okay, for 2113. So like that, because this energy is a function of time period and wave height in case of ocean energy. Now, here, if we see efficiency, if you find out efficiency, because input power, we know there is a formula available which can calculate input power available to the float. Okay, that formula is nothing but a function of wave height and time period. So we can find out input power to the device. Okay, so this is input power available for a particular wave height and time period. And then what is the output power that we have measured using a torque measuring sensor device and a dynamo. Okay, so if you found efficiency, then this is the efficiency, right? Similarly, we can find out for different wave heights. Now, if we see this, if we draw this plot for different wave heights, you see this, what is the influence of wave period on power generation. Now, see from this plot, you can see clearly that power generated is maximum when the wave height is 30 centimeter and wave period is 2.8 second, right? So this is 2.8 second. So maximum wave energy or electricity we are generating from this period. And if you see this, maximum power is generated by mechanical wave energy for a wave period of 2.8 second for all respective wave heights. Okay, what is 18 or 30, whatever is the wave height. So for all respective wave heights, we are getting maximum power at this particular time period. So it is the natural time period which is found experimentally. Okay, so it is the natural time period of the device, right? So there is resonance and we get this enough power from the device. If we see power output as a function of wave height, see this is increasing with wave height. Okay, so it is seen from the figure that there is an increase in the power generated with respect to the wave height. Now, once we did study with this device, then we also carried out an analysis for this device to assess the performance, and we found out certain loopholes there which we can take care, we can fix, and with that fixing we can improve the performance of the device. So what we did here in this mechanical wave energy converter, we did these modifications. First is unidirectional chain assembly is replaced by double rack mechanism with pinion gears having inbuilt one-way bearings. Okay, so what are the reasons for this? Friction losses are high in unidirectional chain assembly. Design is not compact. It is less safe. Okay, so this is what are the benefits? Improved efficiency, compact design, and improved safety. Now it becomes a completely gearbox system. So there is better in terms of efficiency. It is more safe and compact design. Now we also have a RPM multiplier here. Okay, because we need a particular RPM to generate power. Okay, so 1:3 step up pairs of gear are fixed here to enhance the RPM of the device. Now, what are the reasons? Friction losses are more in RPM multiplier. Design is not compact, it is less safe. So what are the benefits? Improved efficiency, compact design, and improved safety. Similarly, we have here rack sports replaced by vertical guide sports. So we fixed roller here with float, because when it is moving up and direction, so it was hindering the movement, freely movements. So we fixed roller to the float and we provided guides to these rollers. So floats was now moving smoothly in upward and downward direction with this modification. Then a flywheel is assembled in output shaft here. You know, the presence of flywheel enables continuous power outputs. You see, flywheel is energy, mechanical energy reservoir, right? So it makes our rotation uniform basically. So it helps us to get smooth and continuous electric power from the device. Output shaft is modified. So no provision in earlier shaft to accommodate flywheel. So we have to update this. Flywheel is accommodated easily. Then stiffeners are connected to the buoy so that it becomes strong. Okay, because sea environment is very hostile. You have seen the video of Pelamis and you have seen waves, real waves coming from different directions and hitting the float, hitting the device. So in this case also, though it is it is strengthened with these things. Now, you see, this is the proposed double rack mechanical wave energy converter. So we replaced chain assembly and I have discussed all the modifications which we carried out to the earlier device. And this is the modified device now. Now, what is the working principle here? During the downward motion of the buoy, this is the float here, there is buoy here. What happens here? Power absorbed by buoy is transmitted to pinion gear 1. Okay, so this is rack 1, this is rack 2. So the pinion gear 1 is here in rack 1, right? While gear 2 remains idle due to inbuilt one-way bearing and vice versa. Power transfer to pinion gear 1 is transmitted to electrical generator, okay, rotating it in clockwise direction through a flywheel and vice versa. Hence, the wave energy is converted into electricity. So just like unidirectional chain assembly, here we have used unidirectional one-way bearings basically. Now, two floating buoys, namely 620 mm diameter and 500 mm height, and 800 mm diameter and 700 mm height, are used to estimate the efficiency of double rack mechanical wave energy converter. Now, output shaft of the device is coupled with a dynamo and a torque measuring device to record the time history of mechanical and electrical power outputs for various wave heights and time periods. So basically, this is totally experimental investigation here, and overall efficiency of the device based on average power produced is thus estimated here. If you see this video, you will get more clarity about the device, which is modified device. see, you have seen with this that with the help of a flywheel, a suitable design of flywheel, the rotation of the torque sensor becomes very uniform. And for a dynamo, basically, or generator, we need a constant RPM system so that we can generate electricity at a constant frequency. Now, if you see this phase lag and heave displacement of floating wire for 30 centimeter 2.5 height, it shows clearly that heave displacement of floating wire is 47% of the wave height. Okay, and it is lagging behind by 58 degree for 30 centimeter 2.5 second wave condition. Now, phase lag for 30 centimeter 2.8 second. Now it is floating wire is 74% of the wave height and is lagging behind by 28 degree. Right. Now, if you see this, this is mechanical output of this device for this time period 2.3, 2.5 and 2.7 second, and this is two wave height 21 centimeter and 24. So see the efficiency. Okay, so this is efficiency, and hence an average there is 6% increment in the efficiency of power generated by this. So if we compare this device with the earlier one, which was based on unidirectional chain assembly, so there is as an average 6% improvement in efficiency. This is mechanical wave energy converter for the same shear state, that is wave period and wave height. So there is almost 6% improvement in the efficiency. Now, average mechanical power produced by this double rack mechanical wave energy converter for 800 mm float is this one. This is mechanical power calculated by using torque sensor output. Now, if you see this, if you talk about this, then see the efficiency here. The hence overall mechanical efficiency of double rack mechanical wave energy converter based on average power produced is 17.4 from experimental investigation. Now, if we see overall mechanical efficiency of double rack mechanical wave energy converter based on average power produced at resonance, it is 23% from experimental investigation as an average. If we say, if you see this video with dynamo for double rack, then you'll get some more clarity. So this was the video with dynamo in place, and we have got a loading system of this bulb, electricity bulb. So we can switch on one by one all, and we can change the load on the dynamo. And based on this variation in load, we have investigated this device completely. What is the impact of load and how does it react to the changes changing loads? Because see, in electricity requirement is variable, highly variable. Okay, so we need to understand what is the impact on the device. Now, this is the time history of electric power generated for double rack mechanical wave energy converter at 30 centimeter 2.7 second without flywheel, and this is with flywheel. So you see this. So with flywheel, it becomes more uniform. Now, it is seen from this figure that power generated is maximum when wave height is 1.6 meter and wave period is this 6.6 second. This is basically for a prototype, and this conversion is done using float scaling laws which are applicable to C devices. Now, if you see this electric power output of the device increases with increased wave height, this is similar for the same device, because with wave height, power available to device also increases. So definitely output will increase significantly. Now, electric power output of the device increases with increase in wave height. You can see this. So this is model, this is prototype. So we have calculated output for the proposed prototype, which can be tested in real C conditions. Now, this is model power, this is prototype power, which can be calculated using the float scaling laws. Now, hence, if we see this efficiency as a function of time period, so this varies accordingly. And at a particular time period, we get maximum efficiency. Okay, so for this device, that is double rack mechanical wave energy converter, it can generate power efficient wave period of 5.4 to 8.2 second and wave height of 1 to 2.36 second meter. Okay, so for Indian conditions, this device is very good, and it can generate electricity for a platform. Local production can be taken care of. Now, what are the major conclusions? Based on the detailed experimental investigations carried out on the scaled model of the wave energy converters, following major conclusions are drawn. Wave energy is harnessed in the heave direction using a floating wire whose oscillatory motion is converted into rotary through appropriate mechanical design. Now, fluctuations in electric power measured at the output shaft are reduced significantly by installing the appropriate designed flywheel in the output shaft of the device. Now, chain assembly, which shows a high risk impactor, is successfully replaced by the double rack mechanism to improve the overall efficiency. Design modifications made in the device enhanced the mechanical efficiency from 13 to 90%. Almost 6% improvement in efficiency was observed by modifying the device. Maximum electric power available at the output shaft of the device is for 30 centimeter wave height and 2.8 second wave period is observed for these C conditions, which is near resonance period of the float. Electric power output of the device increases with increase in wave height, and maximum electric power output of the device with the 800 mm float occurs at 2.8 second wave period for wave heights considered in the analysis. And if we talk about operational wave period of the proposed device is nothing but 5 to 8.2 seconds corresponding to prototype, which is adaptable design for Indian cost. Risk analysis carried out of the device indicates higher operational safety. Failure modes are highly detectable in the improved design, which is one of the major advantages. So we did this risk analysis for this, which I did not discuss in this presentation because otherwise it will become very long. Power available at the shaft of the prototype device is significant for the developed mechanical system and is comparable with other commercial alternatives available at present. Compact design, cost effectiveness, ease of fabrication, and cheap maintenance make the proposed device. So these are the references, and thank you very much for the patience you have shown.
It's a very nice presentation. So, Dr. Nikhil, how you would like to go about the questions that we have?
I think we are having some questions but if anybody wants to ask, after
You can take the questions which has been typed, and then we can go to additional questions.
So, Dr. Harinder, the first question we are having chat box. The first question is how does snake-like movie produces power?
Yeah.
And question in chat box, how does snake-like movie produces power? I think it is the.
Dr. Nikhil, आपकी आवाज clear नहीं है.
Nikhil, your voice is not clear. I am not.
Okay, you can read the question in chat box. Can you see the chat box?
Yeah, 1 second.
Or I can read out for Dr. Harinder if you want.
Sir, please you read out.
Okay, so the question is, sir, how does snake-like motion produces power in your pill schema kind of that snake kind of structure?
Sir, in that structure, basically, you see, let me come to that. You see here, what happens here? In this device, there are 3 hinges, okay? So, in these 3 hinges, these hydraulic rams are there. Okay, when it is going up, there is these sections, they bend upward and downward. When it is bending downward, so hydraulic ram is there in the bottom side, so that is compressing the oil. Okay, when it is bending in upward direction, then there is hydraulic ram which is compressing oil in this direction. So in these both directions, this moment at hinge is compressing oil and generating a high pressure oil. Now this high pressure oil is used now to drive generator through hydraulic rams. So this ultimately in this device we are producing high pressure oil, and that is used now to rotate generators.
Okay, and the other question is, you mentioned in your presentation that this particular device was tested in real life situation for 1.5 years.
Yeah.
But what is the reason why it could not continue for that long? Is it
actually, sir, it failed after 1.5 years. It failed because of fatigue. because sea environment is highly very hostile, and actually waves are highly irregular. Okay, in time, in terms of time period and wave height. So this device could not sustain this fatigue, and it failed because of that. And they tried to work out, but still they are struggling to make a device which can continuously generate power.
Okay, fine. So the next question is in mechanical wave electric converter, how can we deal with the power fluctuation showed by the bulb in the video?
That we have electrical devices which can make that stable, and there are two things which we can do. As far as design is concerned, we can optimize the design of flywheel, okay, for a given range of wave height and time period, and with that we can minimize fluctuation, and remaining fluctuation we can find a solution in electrical technology, where there are systems which can smoothen these fluctuations.
And I think there is one question, I'm not too sure whether this has already been shown, I think in your slide. It says, the question is, with 1:7 scale model, how will this be extrapolated in terms of efficiency? I think that you explained in your last slides, right?
Yeah. Actually, see, sir, for systems in ocean, we have Ford scaling laws. Okay, so by using these laws, we can calculate powers to prototypes. So these laws are designed specifically for ocean devices. For example, for ship, for wave energy converters, and for platforms which we design for ocean.
So another additional question to that, like in sea, can this double rack system can also be employed in rivers, large rivers where the flow is very high?
No. This is not designed for river, because see, if you have seen the video carefully, this float which is attached to this device, it is moving in heave direction. When waves are coming, so they are lifting the device. When crest of the wave is trough of the wave is coming, then device is going down, and when crest is coming, it is going up. Okay, so in case of river, there is no waves generated. Okay, so because there is current, basically current like situation, just like in ocean, there is water flowing in the form of current. So in waves, water is flowing in horizontal direction, and there is no wave like motion. So this device cannot work in river.
Okay. And sir, now there are a couple of questions from my side, and as well as there is one more question being typed, but I think I will link up all these questions. So the Palamis wave energy converter, which was developed, this was developed by which country or which scientist? It was in Europe or somewhere else?
There is a company, sir, Drogan, something like this. Is a Portuguese company, a Scotland company, basically. And it was, I don't remember the name of scientist, particular person, but this company developed this device, and it was developed on industrial scale. And a full scale prototype was tested in ocean.
And this was which year, Professor?
2008.
And thereafter, they have not after studying the fatigue, why the equipment has failed, they have not tried to relaunch the testing?
Yeah, they couldn't come so far.
Okay.
Actually, see, sir, when I was doing my PhD in IIT Madras, a very high level delegation from UK came to IIT Madras for brainstorming.
Okay.
And they were saying that they have said it was in 2012. Okay, 8 years ago. So they had a discussion with all people who were working in wave energy for 2 days continuously. And they set a target, do or die, or you can say now or never. So they said by 2020, we will get 30% electricity requirement of UK from wave only, from ocean only.
Okay.
And they have industrial people also along with this. 7-8 companies were involved with academics people, and they were saying by 2020 we will meet this target. But if we see today also, they couldn't meet this target. So there are challenges in ocean which are more than any other technology. because of environment, because of other challenges, then transferring power from ocean to real means on the land, then there are issues with that. But yes, a huge potential is there, and people are working on that. Many companies in Europe are working on that, and definitely there is hope that someday people will find a suitable technology which can harness this potential available to many countries, especially in Europe.
So this do and die conference which happened with UK team, did they explore or maybe kind of pinpointed on some particular model going forward which can be successful or tested, or it was just a discussion that how
that was a basically brainstorming session. Basically, they came for discussion that if they get some better idea with people who are working in wave energy.
Okay.
And they were talking about this total, basically ocean energy. That includes your tidal and other forms of energy also, offshore wind also. So they did not particular say this technology we will focus.
Okay. So another point which you mentioned in your previous initial slides about the power which can be generated per meter, which says 5 to 15 kilowatt of power or megawatt of power. I don't know if you can. So what was that? Was it the surface length you were talking about, or you were talking about the depth 5 per meter?
Basically front, you can say. See, if you see the design of the float, so what is the diameter of that float? So when wave is coming, just like solar, sir, solar is falling on a surface, right? So what is the area over which solar is falling? Okay, solar energy. Similarly, here also, this device is facing, for example, float. This is having a diameter, and waves are coming. Okay, so you suppose you keep this in a particular area. So what is the front area? So these waves are hitting this front area. So this you have to take this into account.
Okay, so the
per meter you have to take into account.
Okay, so that was the mention you were making per meter. This much kilowatt or megawatt potential is there, and based on that, you calculated the coastal length of India or the global, and calculated how much is the potential
yeah.
for.
In review papers, we can get the details regarding this, that how to estimate potential. And what is the available energy to device, that is the input to device basically. And potential, then various researchers have written these review papers, and a detailed analysis we can find from there that can give you clear idea about this estimates.
Okay. Now, one of the big million-dollar question is that in this this technology has such a high potential and being tested, and a lot of prototypes being filed from last 150, 200 years. Why still now there is no commercial viable solution being developed by the global?
Actually, sir, thing is that I had told you that there are two issues. Most important issue is that hostile environment. Sea waves are highly irregular. I have done my PhD here, and if you see this efficiency of my device, that is around 17-18%. And out of the, and an interesting thing is that this efficiency is for regular waves, which can be generated only in laboratory. When I tested my device for this irregular waves which are in sea, the efficiency reduced drastically, and it was only 4 to 5%. So the major issue is this, that highly irregular waves, and designing a device for this range of irregularity is a very challenging task, number one. Number two is that as on today, finding investor is becoming a challenge now, because cost of electricity generation from other renewable energy sources, just like wind and solar, this has been reduced drastically. Okay, if in India, if you talk about solar energy, around 2 rupees 44 paisa, or maybe 2.5 rupees per unit, we are able to get this power from sun. Now, when we go to ocean, then this becomes significant. So, whatever technology we employ, if we do not compete with other existing renewable energy technologies, then nobody is going to invest in that. So major challenge here is not only design a particular or a suitable device, but also to reduce the cost of, and basically levelize cost of energy. Okay, so cost reduction is another challenge. So there are huge challenges in this domain, and you see that still things are in R&D stage. But once we are getting cheap electricity from other renewable sources, the focus has been shifted in other direction. And here definitely that much focus is not there.
I have a question. Uniform RPM is not an important criteria in electricity generation.
No, uniform RPM is important, sir, because the generator has to rotate at constant RPM to generate, you can say, a particular frequency.
When we generate electricity by using waves, then the RPM will not be uniform.
No, it won't be constant, but uniformity can be improved by employing a suitable designed flywheel. And a little bit non-uniformity will be available, so that can be taken care by electronic devices, which can make this smoothen the curve. So up to some extent we can make it uniform, but 100% you can say a fixed RPM, just like in our traditional methods in steam turbine or gas turbine or diesel generators, that kind of RPM is difficult to attain here. Similarly, in wind energy also, there are issues with this getting constant wind. So, but up to some extent, we can get uniform RPM up to some extent.
Because I feel the variation will be more in case of waves.
Yes, yes. So actually, sir, these are the real challenges which people are facing. In case of irregular waves, this variation will further increase. Okay. So these are the real challenges. People are struggling to find solutions for these. That is the major reason that still people are in R&D stage, and some are testing only prototypes.
So probably I think Rajneesh, what is happening on Professor Saab, that since there are alternate energy options available like solar and wind, which is already being developed and available at a much cheaper cost, so the right resources are not going into this technology to that extent, because there are options available, right? If there would have been no option, probably people would have put their money onto this to make it happen as early as possible, right?
Yeah, resource is available, but suitable technology is not there.
Yeah, that I'm saying like, for example, if alternate energy renewable technologies would not have been there and the world has no other option, so then the all resources technology focus would have gone into this technology probably. I'm saying right now it's more of research happening in this, but not the real money on the table, looks like.
That is true, sir. That is the only thing. Now, investors are not very keen to explore this domain, because for years people are working, and still we are come to commercial scale. So that's the challenge here, and investors do not have that much patience. And in Europe also, in Germany, people are doing wonderful job in solar energy exploration, and that's the major reason.
सो प्रोफेसर साहब, इसमें क्वेश्चन कमर्शियल पॉइंट ऑफ से आता है. कल अब हम जब डॉक्टर निखिल हमें ब्रीफ कर रहे थे, उन्होंने इंडिकेट किया था कि रफली अराउंड इट कॉस्ट 6 crore per megawatt, if I remember correctly, for installation cost of a solar plant or wind plant, around approximately.
Yeah.
And then you are saying the cost of generating energy is close to 2.4, 2.5 rupees per kilowatt, right?
Yeah.
So is there any benchmark corresponding to that? Like if this technology, where this would scale up, I'm saying in terms of both this installation cost, first cost, and the maintenance cost in terms of per unit charges?
In wave energy?
Yeah.
See, sir, if I remember correctly, for Riva plant in Madhya Pradesh, Delhi Metro did this power purchase agreement at 2 rupees 44 paise per unit. For Delhi Metro requirement. This was a PV panel based plant, basically PV plant. Now, if we come to wave energy, there are two issues. Ocean is, I had told you, very hostile. When we design platforms, we need to use best material available, because corrosion is a big factor in ocean. Okay, because ocean water is salty, and then availability of oxygen at the surface makes it highly corrosive in nature. So we need to design platforms which can last for some time, and in that cost is huge. For an average size platform, cost may be in crores, hundreds of crores, 300 crores maybe. So initially, installation cost is huge if you go for a device there, number one. And then other challenges are there. So cost is huge factor here. And then second challenge is getting a suitable technology which can produce power in a range of wave heights and time period. So definitely cost is going to another challenge, but developing technology itself is, people are struggling right now. So that's why there are this improvement, you can say, in this segment, people are still struggling.
Okay. So, sir, there are few more questions being typed. Maybe I would request the like Deepak Dev, one by one they can ask their question. Deepak Dev Bora. If you can unmute yourself and ask your question which you have typed.
This is Deepak Dev Bora this side. So my question is like we have using that oil, compressed oil in snake type.
Yeah.
So I think movement is same, compression movement is same. Can we use the compressor, air compressors? Because air compressor we can store the energy in the form of compressed air, and the compressed air can be used for moving the turbines or generator. So we will be having a less moving parts in case of compressor, because compressor movement is very simple. We can compress the air and store it. Even in the high tides, low tides, all type of waves, we can have a generation of compressed air during the process.
Yes, that can be done. There is no issue, I think. But I think designers and people who worked in that technology, they found this oil medium, working medium, a suitable medium. But you see that compressed air we are using in oscillating water columns. Okay, we are compressing air there and we are using in air turbines. So that technology also been used. And in this particular Palamis, maybe because I am not involved in that project at all, so I feel that designers found oil as a suitable working medium for that application.
Probably air compressor has a very low efficiency.
Yeah.
There are a lot of wastages.
There are a lot of issues in that. So
a lot of leakages of air. So
yeah.
Maybe air will be corrosive also.
Yeah, see, that is a ocean environment. Yes, air will always add in corrosion process.
Okay, so the next question is from Mr. Naveen. Naveen, can you unmute yourself and ask question?
Yes, sir. Sir, my question is, what is the depth requirement for this system? Like how far from the shore we can employ this system in a full scale model?
You see, Parveen?
The question is from Naveen. Yeah,
Naveen. You see, Naveen, there are different devices. Okay, if you classify devices in different category, in terms of their location, near shore devices, on shore devices, and offshore devices. Just like this Palamis device, this is a deep water device, basically offshore device you can say. It is a completely floating device, and it is moored to the ocean bed surface, bed of sea bed, with the help of mooring lines. Then there are devices which can be installed on the shore itself, just like this oscillating water column. So it will be constructed on the shore itself. You go to beach, to there itself. Then there are devices which can be installed in shallow water. Okay, we classify water in ocean, shallow water, deep water, and then onshore. So it depends which kind of device you want to install, right? So then there are floating device, there are fixed device. If you go to deep water, then there is no question of fixed device, because depth is huge, even 3,000 meters, okay, in deeper ocean. So it depends which kind of device you want to install, number one. Number two, then what is the plan? For example, if you want to transmit power to land, then definitely your preference will be onshore devices. Suppose you want to use power generated in platforms already installed in ocean, or maybe other things there only, then it depends which device you are using, and then what is your requirement. So there are two issues. Devices are there already, which people are working, which can be installed onshore, which can be installed in shallow water, which can be installed in deep water.
Okay, sir. Sir, what about the double rack mechanism? Can it be employed on all on deep water, or like can be offshore only?
This can be employed in deep water very easily. If you have a platform, existing platform, for example, you just do minor modification in one corner of the platform and you can install it there. The only thing you have to make sure that as a designer, that your float should get reaction, right? When waves are hitting, so float should get a reaction from the platform. It should not happen that float and platform both start moving in same direction. Then it won't get any reaction and it won't be able to rotate the generator. So it should get a reaction. You can install it in deep water very nicely. Onshore, it won't work because it is a point absorber basically. It is a heave device. So it should get enough depth to have a heave motion.
Okay, sir. Thank you, sir.
Okay, so next question is from Mr. Pranjit Sarkar. Pranjit Sarkar. So if you can unmute yourself and ask your question.
Good evening, sir. Tanjit this side. Sir, my question is, like for the onshore devices, why can't they just use a conventional dam-like tunnel and just pull the water from the sea into the turbine and then discharge it back into the sea?
If you remember, we discussed a device that is called overtopping device. Okay, so this is same concept which you are saying. In that, again, disadvantage is that every renewable energy is, you can say, there is no constant availability of this. Okay, regularity is not there. Just like wind also, sometime it is available, sometime it is not available. And wave energy comes from wind only. If there is no wind, there is no wave energy, then enough water won't come there. So generating power regularly, continuously is a challenge there. But yes, this device is for onshore only. You bring the water by using a particular design to lift this water in the dam, and then you can generate power. But again, regularity or continuous availability of that water is a challenge here.
No, sir, I am talking more about like a tunnel. Means you are on shore, we have a tunnel that just pulls the water. Sir, it doesn't depend on waves. It just pulls the water. Means a
So how
little
you will
deeper.
pull the water? That is the question. You need to spend energy to pull the water. You will either install a pump, or how you will pull the water. That is the question number one.
Sir, I will just give a sliding edge to the turbine. Just like we have in the conventional river dams, the water comes from height and just rotates the turbine and goes out.
There is no height in case of sea, no. In river there is a height available.
In ocean there is no height. You go to beach and you see the structure, see the terrain carefully. You will find that sea may itself, this height is less there. Okay, so water will come forward because of this waves generated. Okay, so it has its own limitation. We cannot pull enough quantity of water on its own, right? But if we make a tunnel and if we install a pump, then we are already then investing energy in that. So what will be the output of your device? I do not know.
Okay, sir. Thank you, sir.
Okay.
Okay, so thank you, Pranjit. So next is one question from Mr. Dev Chug. So Devji, if you can unmute yourself and ask your question. Devji, are you there? Mr. Dev Chug.
Good evening. My question is about the test data that you had indicated. Hello, can you hear me?
Yeah. Yes, sir.
Hello?
Please. Yeah.
Hello?
We can hear you, Devji.
Hello?
We can hear you. We can hear you.
Hello?
Hello.
Yeah, Mr.
Hello?
Dev, we can hear you.
Can you hear me?
We can hear you, yeah.
Yeah, my question is about your test data. Okay. All right. My question is about your test data that showed my question is about the test data that you presented, which shows an efficiency of say 12, 13% or 18%. Have you sort of investigated how that efficiency could be increased? Because that would cut down the cost per unit, so it may become viable.
You, sir, if you see this, I proposed this device first. This is a device that depends upon this unidirectional chain assembly. Okay.
Hello?
When this float is moving in heave direction and going up and down, so we are using gravitational chain assembly to convert this heave motion into rotary motion, and that is unidirectional. So we modified this device with this double rack mechanical wave energy converter. You see, we modified this device by these making so many changes here. And if you see this, we observed this with experimental investigation that there is, as an average, if we see, there is 6% increment in the efficiency of the device. Now, further, if we have to further check what again we can do so that we can improve the efficiency further. I concluded my PhD with these two models, and then further now, if somebody works, definitely further, there is always scope for improvement in any technology.
तो प्रोफेसर साहब आपकी पीएचडी के बाद हमसे द कंक्लूसिव रिमार्क्स फॉर व्हाट I'm saying I have not done the PhD, so I'm just asking a question. When you do a thesis,
yeah.
So to take it to next
right.
level,
Okay.
what
Thank
you do
you.
basically.
Concluding remark is this, sir. Wave energy is definitely available, and you know, on the planet Earth, 70% water, okay, and maximum there in ocean. So potential is huge worldwide. In Europe, in US, Japan, Chile is the number one in wave energy potential. If somehow we can find out a technology which can harness this highly irregular energy, wave energy, definitely it can meet requirement of many countries and Europe especially. So the basic challenge before researchers is that to find a suitable technology first, and then to make it economically viable. You can say competitive with other similar renewable energy technologies. If we can get breakthrough in these two things, definitely huge availability of wave energy is there. So we should hope for that. If we can do that, this will be very helpful to the world as a whole.
Thank you, Professor Saab. If anybody else has any other question, please feel free to ask before we, because it's already, I think.
If you even get further questions, you can write me a mail. I can share my email ID with you. So you can write me a mail. I can share with you relevant papers.
तो आप निखिल जी से निखिल जी से आप शेयर कर दीजिएगा तो हम
sure.
ले लेंगे.
I will
ये जो
share
presentation है, आप can you share this presentation, part of it or full?
Definitely, I will share with you.
Okay, thank you.
Okay. Thank you very much.
So we are thankful to Dr. Harinder for his memorable talk. Thank you, participants, for taking such a nice interest in the talk. Thank you, sir. Thank you, everyone. Thank you.
Thank you.
Thank you, everyone.